right, today's notes are on verifying trig identities, which is actually trig proofs. So some simple things we're going to work on together and talk about how to go about them. Sometimes the way you would do it might be a little different the way your peer would do it or pick it up, and I'll explain that in just a minute. But you've got to know your identities. Using your trig identity sheet is going to be very important. You're wanting to start with the more complex side, and that's where things, you may think something's more complex than someone else, and you start with a different side, and that's okay. It's just a little bit easier to think about how can I manipulate one side or another to prove it's the other. So you're not changing both sides, you're trying to prove that these things are equal. You want to express everything you possibly can on whatever side you picked to be in sine and cosine to get it to equal out. And then you'll use factoring, expanding, simplifying, reducing to be able to prove these. So we're going to start with a sample, and this one here is, notice it's an equal, so we've got one side equal to another side. We're going to pick the side that looks most complicated, and that's what we're going to manipulate and change around to see if we can make it match the other side. So I have a bunch of little terms on the left side, but not on the right, so I'm going to leave this part alone. So my goal is to try to prove that this complicated side, the left side, is like tangent of theta. So I'm going to think about what I'm going to do. So when I start here, I'm going to look at, okay, well, cosine's already written in cosine. That's pretty simple. Secant is left. So let's see if I can write that in a form of cosine or sine. So cosine stays. Secant we know we can write as 1 over cosine of theta. And then cotangent can be left alone for a minute, okay? So what we're doing is we're just using reciprocal identity properties, okay, first to rewrite this top part, okay? We're never touching the other side with tangent. So we're now going to go ahead and see if we can simplify cotangent down. So when we have here at the top, you can think about this cosine of theta over a 1 and 1 over cosine, they would actually reduce down to 1. So what I have is 1 over cotangent. So I know that 1 over cotangent is also going to give me the reciprocal of tangent. So I can be done there. I know that that can be the same thing as tangent theta. Now, if I didn't see that first off and I rewrote this cotangent down here as cosine of theta over sine of theta, and I had the 1 on top, this is the same thing as saying 1 times sine of theta over cosine of theta. I multiply straight across, I still get just sine of theta over cosine of theta, which I know is also tangent of theta. All right, so look at B and decide what you would pick as the most complicated side and start with that. Or, and this may be different from what I pick. All right, so when I look at the left side, that looks really simple, sine and tangent. Sine's already in sine, tangent's not, but I can rewrite it pretty simply. The other side is not written as simply, it looks a little more complex. However, for this time, I'm going to show you that if I pick the one that wasn't as complex, now it has some movement that has to happen. It wasn't like our first one, tangent. But I'm going to pick, I think, this side to leave alone, even though it looks a little bit more complex. And I'm going to rewrite this side. So sine can just stay as sine. And I'm going to write it as a fraction just because the other side's a fraction. So sine of theta over 1. And then I'm going to be multiplying it. I want to rewrite tangent of theta. So I can rewrite tangent as sine of theta over cosine of theta. And then I'm going to multiply those. So what I get is sine squared of theta over cosine of theta. Now, if I notice here that what I'm trying to get to is cosine here on the bottom, cosine here on the bottom, already there. So how does this sine squared theta equal the 1 minus cosine squared theta? Well, we have a Pythagorean identity, so we can rewrite sine squared theta as 1 minus cosine squared theta over cosine theta, and these are identical. So that is proof. See? And again, we're going to pick the side that we want to write. And I'm going to kind of stick with my plan I've been doing here, and I'm just leaving this side alone. That's not always happening. I'm just leaving it alone. I'm just deciding to do that one. So I'm going to rewrite these as simply as I can. Now, I know I need to get it to be to 1. And so I got to think, what can I rewrite stuff over here to get to a 1? And then I have sine here, and I have it squared, but I have 2 of them. So I've got to think about that. So if I think about how I can rewrite cosine squared just itself, I can rewrite that as 1 minus sine squared of theta. That equals cosine squared of theta. And then this is minus sine squared of theta. Now, if I look at combining this negative sine squared of theta and this negative sine squared of theta, I have 1 and I have another one. So I actually have 2 sine squares of theta, and then the sine stays, because it's not multiplying, it's just combining. 1 comes out front, and now this matches this. The last example in our notes, I want you to pause and see if you can do it, and then check back. So I decided to, again, I'm just going to leave this side alone. Notice I'm not touching those sides I leave alone. I'm trying to get my other side I'm manipulating to match. So secant is not in cosine or sine form, so I'm going to rewrite it as 1 over cosine of theta, and then minus cosine of theta. Now, I want to be able to combine these, and these I can write this as a fraction, and they're subtracting, and they're fractions, but they have unlike denominators. So I need to get common denominators. So I'm actually going to multiply both of these to get the common denominator with cosine of theta over cosine of theta. So I'm just multiplying basically times 1, our property there. And so what I get up here, once I can do that, is I have a common denominator now of cosine theta on the bottom. And then on the top, because I multiplied it here, this turns into a square. So it is 1 minus cosine squared theta. And that 1 minus cosine squared theta actually equals sine squared theta, because that's Pythagorean identity. And then the cosine stays on the bottom. Now I'm trying to get to what's highlighted in yellow. So if I think about what's happening here, I've got to get them to look the same. So I'm actually going to separate this sine squared into 2 pieces. So I'm going to do one is sine of theta, and the other is sine of theta. And they would both be split up. So if I multiply them back, I get back here. But I can't say cosine on the bottom, cosine on the bottom, because that would give me something different. Cosine can go on the bottom of 1, but the other one would have to be 1. So think about if I multiply back sine and sine, I get sine squared. If I multiplied 1 times cosine, I get cosine. So you have to think about what's happening here. Well, we know that sine of cosine of theta actually equals tangent of theta. And I'm multiplying, and sine over 1 is just equal to sine of theta. And even though this is sine first and this is sine second, they're still multiplying, so it doesn't matter. It's the same thing. Tangent being first or second when multiplying doesn't matter. So now I know that I've proved that they're the same.